Hello and welcome to Real Civil YouTube channel. In this video, we are going to talk about capacity based seismic design, the philosophy behind most modern seismic codes, and how it has evolved into what we call probabilistic performance based design. So, this is what we are going to cover in our today's presentation. Uh, First, we will see the old approach, that is strength based, and versus the new performance based design. We'll also cover the capacity curves and ductility. Then we will cover the probabilistic assessment framework, and we'll make separate video on how to build the fragility curve. Okay, because it will take time, so we'll try to cover these 3 points in our today's presentation. So let's begin. The traditional approach, or we can say the old approach, is strength based design. So before we talk about performance based design, let's look at what most codes, including the IS 1893, that is the Indian Seismic Code, still use the traditional strength based design. Okay, so sorry. So in this approach, what we do, we basically calculate one force. Here you can see the formula VB, that is base shear, using a standard formula Z by 2 I by R SA by G into W, and we design our structure we design our structure to resist this one force, and if it can resist it, we call the building safe. Okay, and most of you know this formula. Now you may have question, what is the problem then? So the problem is, here you can see, the structure is designed for a force lower than the actual seismic demand, because here in the formula you can see R is there, that is a response reduction factor, and this response reduction factor for OMRF it is 3, and for special moment resisting frame it is 5. Okay, and here we are dividing by 3 or 5 for OMRF or SMRF building. That means we are reducing the force, and we are designing for only 20 to 30% of the true earthquake force. Okay, so this is not the actual force, this is the reduced force. Actual force is something else, and we are designing just for 20 to 30% of the true earthquake force. Now you may have another question in your mind, that why reduce it? Okay, so here you can see, uh, actually the philosophy is, here you can see this is the actual force, earthquake force. Okay, but we are applying some reduction. Okay, that means we are designing just 20 to 30% of the force, and this is our design force. Okay, as this design force is lesser than the actual force, that means our structure is going to yield. Okay, and we want our structure to yield. We want our structure to yield and enter into inelastic range. Okay, so this is the yield, and beyond this yield, this is the inelastic, and this is the elastic phase. Before yielding it is elastic, after yielding it is inelastic range, and we want our structure to yield, because the when our structure yields, or that inelastic, the cyclic behavior is what dissipate the seismic energy, and in elastic behavior it doesn't dissipate much energy, it's non-cyclic. Okay, so inelastic, when our structure enters into inelastic phase, then it dissipates more seismic energy. So there is a gap. Okay. So what is the gap? That strength based design tell us whether structure resists the design force or not, but it doesn't tell us about the damage pattern. It does not tell about failure progression. It does not tell about the real performance of the structure. As we know that our structure is going to yield, it is going into inelastic phase. Okay, then how it performing in that inelastic phase? That is what the strength based approach does not tell us. So here you can see damage pattern, means we have no idea about how actually structure is going to deform or degrade. Failure progression, we have no visibility how the structure is going to fail, which member is going to fail first, and how the failure progress. We don't have any real performance here. We can't judge the stiffness, we can't judge the ductility, energy dissipation. Okay, once the structure yield. And that's why the performance based design came into picture. This performance based design fill this gap. Okay, now I'm going to explain you about the performance based design. Here you can see this is the title, performance based design. And this basically focuses in the inelastic range. This focuses more in inelastic range because that's where our real structure collapse happens. And the basic idea behind this is a structure that deforms more after yielding is more ductile, and ductile structure dissipate more seismic energy. Okay, that means the basic idea is we want our structure to deform more in elastic range without collapse, and that we consider is more ductile, and ductile structure dissipate more energy. Here there is one graph I will explain you. So this first graph is of old building. Here you can see this is how this building behaves. Okay, so you can see that it is a brittle failure because after uh, the structure does not yield. Suppose this is the yield point, it does not go much beyond the yield, and it suddenly loses the strength. That means the structure is brittle and fails right after the yielding. So this is the yield point, and it fails here, right, and dissipate very little energy. Now you can focus on this graph. This is the second, that is new building but poor ductile detailing. Again the structure perform well, and then in inelastic range it resists little but again fail abruptly after yielding. Okay, so this much is the inelastic range of the structure, and it again fails abruptly. Okay, now you can focus on the green color, that is third, new building but designed with modern codes with ductile detailing. And the expected behavior, you can see it has resist much larger force, and it has deformed large in elastic range. It deforms a lot after yielding, and it dissipate most of the energy, and it resist large forces overall. So this is this behavior we expect, the the one which is shown in green color, large force to be resist, and there should be large inelastic deformation should be there before failure. We can say the failure may occur in this range, but this is quite big range where structure yield and dissipate the energy. So this is what the performance based design reveals. This basically gives us the idea about elastic and inelastic response. Okay, so we can study both elastic as well as inelastic response. We can see the failure type. That means the particular member is failing in flexure or shear or in axial. Okay, we can get this information also. Then we can get the sequence of failure across the structure. That means the structure is failing from bottom up or top to down. Columns are failing first or beams are failing first. This information is also can be achieved from this performance based design. Then ductility capacity. We can get the stiffness in both elastic as well as inelastic range because now we have the capacity of the structure. Then we can determine the energy dissipated during the earthquake. So all these information is we can get from this performance based design, and which is not possible in strain based design. Now the application of the performance based design is for both existing old structure as well as the new critical structures also. In old structure, you can identify the local or global weaknesses. So where the structure is weak, then we can improve that, or we can decide what kind of retrofitting strategy should we go for. And using this retrofitting strategy, we can improve the performance of the structure. So basically, with the help of this philosophy, we can identify which columns, which beams, which joints are weak, and then we can work on it and we can improve the performance of the old structure. In case of the new structure, for example, the structure those have very much importance after the earthquake, like hospitals, power plants, those structures with high social importance, we can raise their performance by uh, designing using the performance based design. Okay, now here you can see before 1990, before 1990, strain based design was the only real practice worldwide, and PBD existed but wasn't taken seriously. So there was PBD, but it was not taken that much seriously. But after the 1994 Northridge earthquake, a historic code changing event where both the concrete and steel building collapsed with the brittle failure observed at the beam column joint. And this pushes the codes like ATC 40, FEMA 356, ASCE 41 to formally adopt performance based design. But this performance based design theory also has gaps. It doesn't fully account the uncertainty. Now you may ask what type of uncertainty. Okay, so there are basically two types of uncertainty. First one is the ground motion uncertainty, and second one is the capacity uncertainty. So let's see what is ground motion uncertainty. So that means we cannot predict the future earthquake frequency, duration, or amplitude. So this is uncertainty. And second, the capacity, that concrete and steel or whatever structural behavior aren't fully deterministic. Actual response is very hard to pin down. And this is where the probabilistic assessment framework came, or the probabilistic performance based design comes in. So there are basically four steps in the sequence. The first one is the hazard analysis. This is the first step, hazard analysis. The second step is structural analysis. The third step is damage analysis, and fourth step is loss estimation. So here we are going to stop. I will just explain these 4 points and we'll stop, and the next video we'll see how we are basically developing the fragility curve. So hazard analysis means here we are dealing with this that particular site where the structure is located, the seismicity of that structure, or the past earthquake, what is the soil type. So these things we study in hazard analysis. In structural analysis, we perform a nonlinear modeling and analysis of the structure using some softwares. For example, SAP 2000 is there. Then in damage analysis, we actually quantify the damage against some threshold values. We'll discuss this in detail in our next lecture. And then the last part is loss estimation, where we translate the damage into some risk or some loss, and output of this four steps is the fragility curve. Okay, so in our next uh, video we'll see what is the fragility curve, what is the formula, and how to make these fragility curves. Then we will discuss in detail about the structural analysis, that is non-linear modeling. So all these points will be covered in our next video. So please like, share, subscribe the channel. Thank you so much for watching.